The real strength of thinking about motion in terms of parametric curves is how it can let you decompose complicated motions into simpler pieces and then put those simpler pieces together to get a full description of the bigger, complicated motion. A sort of classic example is this one. So suppose we have a wheel rolling along the ground, and this wheel will have radius 1. Let's parameterize the motion of a spot on the wheel that starts on the ground. So right here's the ground, here's our wheel, and there's this spot on the wheel. And as the wheel rolls along, right, after a little while, this spot, since the wheel is going this way, after a little while, this spot will have moved up to here, and then the wheel keeps rolling, and the spot that's turning this way, and so the spot rotates over to here, and then down to here, and so on, right, like this. So this spot is going to somehow swing up to here, and then at some point it's going to be at the very top of the wheel, and then it's going to swing back down to here, and something like this. So we get this sort of arch shape. This shape is called a cycloid for, I don't know, traditional reasons, because it's a wheel rolling along. It's a cycle somehow. So let's describe let's see if we can come up with a parametric curve that describes how this point is moving around the plane. I guess the first job is to choose a coordinate system, and just to make things easier on ourselves, let's choose a coordinate system so that the origin is where this point starts out. Now it's kind of hard to know where to begin if you think about just this entire motion of this point. It's not a shape that we recognize really, right? Because after it reaches this point, at some point it's going to touch the ground again, and then it's going to take off again like that. And this isn't really a shape that we recognize, so we don't have any sort of built-in formulas tucked away in our brains somewhere to describe this shape. So we're going to have to come up with something somehow. But the one thing that maybe we can realize about how this motion works is it's actually made up of two pieces. On the one hand, there's this point on a circle, and since the circle's rotating like this, so there's this point moving around a circle about the center of the circle, and on the other hand, as it moves, the center of the circle is moving sideways. So let's try to write down those two motions separately, and then maybe we can just add them together. So let's think about this rotation. Now, on our coordinate system, right, the center of this circle is, since the bottom of the wheel is just touching the ground and the wheel has radius 1, that means the center of this must be at 0, 1. Okay? So the center of the circle is at 0, 1, and we're starting at the bottom, and we're going clockwise around this circle. So we can write down parametric equations for this circular motion. So the x-coordinate starts at 0, so we should use a sine function, so sine of t. And it's starting at 0, but it's going negative, so we need a minus sign. And the radius here is 1, so right, there's a hidden times 1 in there. And also the center of the circle is at +1, so we need a +1 right here. Oh, no, that's not. That's in the y direction. In the x direction, the center of the circle is at 0, so we don't need to add anything to the end of our x-coordinate function. Now for our y-coordinate function, our y-coordinate starts at -1, or starts at the bottom of a cycle, right? The y-coordinate starts at its most negative extent, and to make that happen, we need a minus cosine. But the center of this circle is at +1 in the y direction, so we need a +1 right there. Okay, so these two parametric equations here describe the motion of the point around the circle. Now we need to figure out how to describe the motion of the center of the circle as it moves to the right? Well, if you think about how a wheel rolls, what really determines the position of the center, right? The thing about a wheel rolling is that the angle that the wheel has rotated through is related to how far the wheel has moved, right? If there's no relationship between the angle that the wheel has rotated and the distance that it moved, then the wheel could move any distance without rotating at all. And that wouldn't be the wheel rolling, that would be the wheel being dragged along the ground. So the thing that makes rolling is that the distance that the wheel moves is the same as the arc length through which it has rotated. So that's sort of what makes rolling. It's that there's no slipping. The wheel doesn't slip at all, so when it rolls from one position to the other, like that distance along the ground is the same as the distance along the wheel. So what we need to do to figure out the position of the center of the wheel at time t, we need to figure out at time t how far has this wheel rotated, or what is the arc length along the perimeter of this wheel as it's rotated through an angle t. Well, the height of the center of the wheel is 1, so that one's easy. But what about the x-coordinate? So, right, we need the distance that this has moved, which is going to be our x-coordinate there, has to be the same as the arc length along the circle, but this angle through which the wheel has rotated, we're calling that t, because that's what we put in here for the angle in our trig function. So that's t. So now we need to know, in a circle, what is the relationship between the arc length around a circle and the angle that the circle has rotated through. So the arc length is, S is the traditional letter, but remember this arc length here is going to be the same as our x-coordinate, so we can write x for the arc length. And the angle, we're calling it t. So what is this relationship here? Well, for a circle, the arc length around a perimeter of a circle, when you've gone around an angle t, is just the radius times t. And this is a unit circle, so we get x equals t. So this x-coordinate here, it's actually just t. All right. So now we know that the center of, the edge of the wheel, this point on the wheel that we're watching, it moves around the center according to these parametric equations, but then the center of the wheel is moving according to these parametric equations. To put these together, we can just add, right? Essentially what we're doing is starting from the origin of the coordinate system, first you go over to the center of the wheel, that is the second set of parametric equations, and then from the center of the wheel, then you use the second set of the first set of parametric equations to move from the center of the circle to wherever that point has moved to around the edge of the wheel. Okay, so to add these two together, we get, so adding the x-coordinates, we get t minus sine t, and then for the y-coordinates, we get, okay, I guess what I have written down here is actually how far the center of the circle has moved, and it hasn't moved at all in the y direction, right? In the y direction, the center of the circle is still at height 0, or still at height 1, so since it hasn't moved in the y direction, I don't need a 1 here, I need a 0. Okay, so putting these two motions together in the y direction, we get just 1 minus cosine t. Okay, so this is a parametric curve that traces out the cycloid. To see that it actually works, let's graph it in GeoGebra. Okay, so in GeoGebra, the command to graph a parametric curve is creatively called curve. Then you enter your x-coordinate function, so that's t minus sine of t. And then your y-coordinate function, 1 minus cosine of t. Then you have to tell it what the parameter is, and that's t. And then you have to tell it what values of the parameter you want to use. And I don't know, let's imagine our wheel has been rolling for a while, so let's go from minus 10 pi up to plus 10 pi. And there we go. There's the cycloid. You can see that when the point is touching the ground, it actually stops moving from side to side just for a moment. And that makes perfect sense because when the point is touching the ground, remember the wheel isn't sliding. So at the contact point between the wheel and the ground, the contact point shouldn't be moving side to side at all. And so that's why when this point that we're watching is touching the ground, it can't be moving side to side because otherwise the wheel would be slipping. But we know the wheel isn't slipping because that's the definition of rolling on the ground. It can't be slipping. And of course the highest point this point that we're watching, the highest spot it gets to is up here. And that's at height 2 because remember we had a wheel with radius 1 and so the diameter across the wheel is 2. So the highest point is at height 2. Another thing to notice is that our wheel, the point that we're watching, it comes back to the ground here. And how far, we could ask how far is the wheel rolled at this point? Well, it's rolled from x position 0 over to, it's a little bit more than 6, so that's 2 pi. And that's exactly the circumference of a wheel with radius 1. The circumference of a circle is 2 pi times the radius, and we had a circle with radius 1. So the circumference of our wheel is 2 pi, and sure enough, that is exactly the horizontal distance that the wheel rolls when it goes around once, 2 pi. So you can see that thinking in terms of parametric curves let us decompose this complicated motion into a series of simpler motions, which we could then put back together to get a parametric curve that describes the full complicated motion.